which of the following gives the area under the curve? And the curve is y equals 1 over 1 plus x squared. And we're going between 0 and 1. So we have a bunch of limits. And remember that right now our way to find area is as limits. So these are all Riemann sums. But one of them will actually give us the area, and 4 of them will not. A, B, C, D, or E. The only difference, by the way, is what's in the front. So which one is it? And it's okay to guess. B is not a bad guess, but it's not the best guess. What? D? D is a better guess, yes. Now, B is very tempting because normally you would have a 1 over n. That's true. That's what's in the generic expression. But you have to think about the whole expression. So this is the variation where we're assuming a equals 0 and b equals 1. So it's 1 over n. That's your width. And f of k over n. So you put in k over n into your function. And then you see, well, you have a fraction and a fraction. That's not cool. So you say, well, you can multiply top and bottom by n squared, and then you don't have a fraction and a fraction. And then, oh, whoops, there's a typo here. That's all right, I can fix it. Then you can pull the n squared out, and that gives you just an n in the front, because n squared over n leaves you with the single n upstairs. And there we go. Cool. All right. Well, this might be one of the last times we see Riemann sums, because we're trying to move towards a better place. All right. Thought for today, courtesy of Eleanor Roosevelt. You gain strength, courage, and confidence by every experience in which you really stop to look fear in the face. You're able to say to yourself, I lived through this horror. I can take the next thing that comes along. You must do the thing you think you cannot do. Courses are challenging, especially as we move closer to the end. And things get harder. But you gain that confidence, that strength, by trying and doing things. And I think you're highly capable. You're very good. You're the students who come to class. I'm really happy that you're here. I believe in you. And I think that you're going to do wonderful things, and you can stretch yourself. And we've talked about some of these ideas before. You know, you have to get comfortable with being uncomfortable. You have to push yourself. And that's how you'll grow. All right. Now, what's today? Well, today we're going to talk about what we call definite integrals. So we know that we can find area by doing Riemann sums. And we say, well, suppose we succeed. We found our area doing a Riemann sum. And if we can, then we say, great, we'll call that integrable. And we'll have a notation for it. So here's our Riemann sum. And our shorthand is the integral sign, same integral sign we use for indefinite integrals. But now we add endpoints. So previously when we did indefinite integrals, or if you like, antiderivatives, there were no numbers here. Now these are numbers. And so a to b, f of x dx. And you'll see things are matching here. So the summation is supposed to correspond to this integral symbol. In both cases, you're thinking of it as adding things up. So we use the sigma. It starts with s. And I like to think of this symbol as you've taken the letter s, you've put it on one of those medieval racks and stretched it, very, very long. So it's a very tall s. S for sum. You have your function, and the dx is acting as a width. Now, I will say this is how we write integrals. There's one thing that we don't write down that's sort of hidden. And this will come into play next week, so I want to point this out. When we write a to b here, what we're secretly writing is x equals a to x equals b. We almost always suppress that because we say we understand that these correspond to x values, but it's helpful to understand that they do sometimes. To emphasize, oh, we're going from x equals a to x equals b. And we'll see why that's important next week. Now, we've now seen two types of integrals. You have indefinite integrals, antiderivatives, that produces a function. We have definite integrals, that produces a number, which we can think of as area, but we can think of it as other things as well. So right now, not so obvious that there's a connection. Spoiler alert, next time is when we actually say, ah ha ha ha, they're the same thing. What? That's crazy. But that's next time. Today we want to focus on just understanding the definite integral. All right, so we're going to go through and talk about properties. So we'll start with the first property. If we integrate from a to a of f of x dx, we get 0. Well, does that make sense? What do you have? Your start and stop is the same place. So if you think about it in terms of a function, you can just grab a piece of paper here and make a function up. What's going on is we have a curve, and we're starting and stopping at the same place. There's no width, no area. There's nothing to see here. All right, so that's property number one. That one's not too surprising. Property number two. If we go from a to b of f of x dx, it's the negative as if we went from b to a of f of x dx. Which is to say, there is an orientation. And calculus actually hinges on orientation. This is especially true once you hit Calc 3. So even the number line we think of as having an orientation. So we talk about going to two directions. You have a positive infinity and a negative infinity. And so when we talk about our bounds, well, when we think about going from a to b, we start at a and we take steps in a positive direction to get to b. But what happens if we're going from b to a? What kind of steps are we making? Making negative directions. We're going in the opposite way, which means we're changing the signs. So keep track of orientation. All right. Next one is that integrals are linear. So if you integrate from a to b, some constant c times f of x plus some constant d times g of x dx, then that's equivalent to breaking it up into two pieces using the plus sign and pulling out the constants in front. Now, why is this true? Why are integrations linear? It boils back to where integration comes from. It comes from sums. And you can do this with sums. Anything that's true with sums is true with integrals. Sums are linear, so you can break them up. All right, so I don't think that one's too surprising. Now the fun one. Suppose we're integrating from a to b of f of x dx, and then we're going from b to c of f of x dx. The claim is, well, that's the same as going from a to c. Now notice what happens here. You have here, there's a b, and it's matching with that b. So it's like, oh, go first from a to b, and then go from b to c. It's the same as going from a to c. That's very believable, right? Let's think about what's happening here. Oh, well, spoiler alert, this is what's coming next. All right. So draw our function, A, B, C. And what do we have? Well, A to B, that's our area here. And then B to C is this area here. And then we talk about A to C. It's like, oh yeah, sure. Areas add together, no big surprises, nothing to see here. Or is there? Well, maybe there is something a little curious going on. What assumptions are written down here about A, B, and C?
That they're all next to each other? Or like the two segments are next to each other?
Well, in some sense, the segments will be close because they share B in common. But there's sort of this implicit like, A comes before B comes before C. But does that have to be true? What would happen if now they were arranged in a slightly different order? So here's A, and then C, and then B. Is this still true? Yeah, it's true. So we're saying that if you add the integral from A to B, which is this whole thing, and then you add the integral from B to C, which is this piece, that it equals that part? Why? Right, that's where orientation comes back into play. Orientation, if I'm going the wrong direction, says you're subtracting. So because we look at here, A to B, and then B to C, that's in the wrong direction. So it's like subtract out this piece. So the end net result is A to C. So this is true regardless of how A, B, and C relate to each other. And so that's one of the advantages of having orientation. If orientation didn't matter, this would not be true. So score 1 for orientation. All right, the last part. And this one seems a little strange, but it's going to be a useful application here. It says, suppose we have the following. Our function is bounded between two numbers, little m and big M, on the interval from A to B. Then it must be the case that little m is less than or equal to 1 over b minus a, integral a to b of f of x dx, which is less than or equal to big M. What's the intuition? Well, let's look at a sketch. So we have our function, and we have our a and b. So let's say this is a, and let's say this is b. Now, we're told something about the function. So we say we want something which is always below the function, that's m, and we want something which is always above the function, and that's capital M. And now, let's compute some areas. Let's start with this small area. How much area is in that rectangle? Give you a hint, it's a rectangle, which can help.
B minus a times M.
Yeah. So this part here, b minus a times m. Now, suppose I looked at not that rectangle, but a bigger rectangle, so all the way from capital M down. Then what's the area of that rectangle, the big one, the whole thing?
B minus a capital M.
Yeah, b minus a times capital M. And finally, the last thing that we want to look at in terms of area is the area. So we're thinking of the integral as being the area under the curve. And now you just say, well, look, I've got three areas. The smallest area is contained in the medium one, so b minus a times m, that's the small rectangle. That has less area than the integral does, which is the area under the curve, which in turn is completely contained inside this bigger area, b minus a times capital M. And now divide everything by b minus a. All right, so there's the result. Highly believable, yes? Good. So any questions on our various properties? All right. Well, let's try a few things. Find the following, the integral from 1 to 5 of f of x dx. But we're given a few facts. We're told the integral from 1 to 3 of f of x dx is 6, the integral from 2 to 3 of f of x dx is 7, and the integral from 2 to 5 of f of x dx is 3. What can we do? Can we do anything? Is it possible? Let's think about what the integrals are doing. So what's the interval for the first integral? Where are we going from? 1 to 3. So 1 to 3. What about for the second one? From 2 to 3. So there's 2 to 3. What's the last one do? 2 to 5. So these are the three intervals that we know what happens in terms of the function. So the question is, can we combine this information to help us? Any ideas? Okay, so there's a suggestion that says, hey, look at these last and first ones. If you add 1 to 3 of f of x dx, and you add 2 to 5 of f of x dx, then what have you done? Well, you've done a pretty good job. You've covered everything from 1 to 5, except you've over-counted in some case. So you need to account for this part here. And how do you account for that? Subtract, because you did it twice. So 2 to 3 f of x dx. And this works great. What does that turn out to be? 6 plus 3 minus 7 are 2. Now there's another way to think about what's going on here. So integral from 1 to 3 of f of x dx. Now let's take this integral. But you see the minus in front? What can we do with that minus? We can change it to a plus and flip the order. Yeah! Beautiful. So this is plus integral 3 to 2 of f of x dx. Right, that's the middle integral. Add 2 to 5 of f of x dx. Now, what's going to happen? Well, that 3 matches with that 3. And this 2 matches with this 2. So what we can do is we can string these together. So this becomes the equivalent of doing 1 to 5, because the bounds are matching. And so it's the same computation. All right. So we can combine integrals. Even if we don't know what they are, we can use facts about properties of definite integrals to put things together. Okay. Let's try another problem. Find the integral from 4 to 7 of 5 f of x minus 3 g of x, given that we know the integral from 4 to 7 of f of x dx is 7, and the integral from 4 to 7 of g of x dx is 11. What can we do? Split it up using what? Linear. Yeah. We can use properties of linear. So we have an addition or subtraction going on. We also have constants. And so that says, hey, we can pull things apart. So this is the same as, pull the 5 out, integral 4 to 7 f of x dx, minus the 3, that pulling out the constant, integral 4 to 7 g of x dx. Well, do we know what the first one is?
Yes.
What is it? 7. Do we know what the second one is?
11.
11. So what do we get? 35. Subtract 33, which is 2. All right. So we've now had 2 problems in a row where the answer is 2. I'm starting to think that may always be the answer. Well, we'll find out if the third problem also has a 2. All right. So the third problem we'll do is this one here. But before we get to it, we're just going to do a small detour and talk about symmetry. So we've talked about symmetry before, I think. If not, you've seen it before. There's certain functions which have wonderful properties, and we give them special names. So we have what are called odd functions. Not because they're unusual or strange or weird, but rather they have a certain type of symmetry. And namely, a function is odd if f of negative x is negative f of x. Now, what does an odd function look like? Well, essentially, an odd function will have some shape like this, to the point where if you can imagine taking and putting a pin here and you were to spin it 180, it would look the exact same. So there's this symmetry going on. Now, what are examples of odd functions? X to an odd power is an odd function, and that's where it gets its name. But it's not the only odd function. Sine is odd, tangent's odd, arctangent's odd. A function is even if f of negative x is f of x. So the value you get on the positive side is the same as the value you get on the negative side. So this has a symmetry where you can just flip it right across the y-axis. So here we're just flipping back and forth. Here we spin 180. All right. Well, what are examples? X to an even power is an even function. Cosine of x, absolute value of x, secant of x. There are others. Most functions are not even or odd. Like e to the x. It's not an odd function. It's not an even function. So when you have symmetry, that's a nice thing to have. Okay. With that detour aside, we're asked to find the following integral. Integral from negative 5 to 5 of t cubed divided by 1 plus sine of t squared plus t to the 4th. Now this is a case where the more calculus you know, the harder this problem gets. So if you know a lot of calculus, what is it you're trying to do right now in your head? Anyone willing to confess? Oh, that's a bold move. Now, you could do some interesting power reduction there. But in general, you're probably like, I got to find an antiderivative kind of thing. And like, that looks pretty hopeless. For people who have had calculus before, this looks hopeless. But I'm here to tell you, it is hopeless. Most of the time. But there's something fishy going on. Why did we do our detour here? What's true about this function? And why did Steve forget to write the dt symbol? All right, let me fix that. Okay. So, what's true about this function? Is anything true about it? Is it odd? Well, I mean, it looks odd. How can we tell? So if we call this f of t, then let's just check f of negative t. That would be negative t quantity cubed over 1 plus sine of negative t quantity squared plus negative t to the 4th power. Now if I take negative t cubed, what's the end result? Yeah, there's a negative. So I'll put that negative in front, and there's a t cubed. Now what happens when I square negative t? Yeah, it's still t squared, though. What if I take negative t to the 4th? What is it? Still t to the 4th. So what do we have? Negative f of t. So this is odd. Okay, but how does that help us? Well, now let's think about a picture. If you have an odd function and you go from, let's say, negative b to positive b, what's going to happen? What's true about these pieces here? Well, they're not quite the same. They're almost the same. They have the same magnitude, but how do they differ? Different signs. So, what's true? If you integrate negative b to b of something odd, you get 0. Because these parts cancel. So what's the integral turn out to be? 0. Classic, sometimes when things look bad, maybe they're not so bad. As the saying goes, it's darkest just before it goes pitch black. Oh wait, no, that's not the saying. Okay, different saying. All right. Now what about for even? Is anything happen for even? So suppose we do something similar downstairs. Negative b, positive b. Now what happens? So from negative b to 0 is the same as 0 to b. So it doesn't cancel, but we get that negative b to positive b of something even is the same as going 0 to positive b of 2 times that even thing. Now, that might not seem like a lot of work. However, there's an important mantra to keep in mind. Whoops. That's supposed to be an arrow. 0 is our friend. We like 0. And any time that you can involve 0, you should do it. Because 0 has a wonderful way of simplifying many expressions. So, all right. So if you have odd symmetry, and keep in mind, you have to have negative b to b, you get cancellation. If you have even symmetry, you can cut it in half and go 0 to b, but remember to double. Okay. So, any questions? All right. Now, definite integrals are about areas. So we can use geometry to find definite integrals. So consider the following function. Our function is 1 from -1 to 1. So that's this piece. X from 1 to 3, so this goes up. And then 3 minus the square root of 4 minus x minus 5 squared from 3 to 7. Now that looks scary. Do you recognize this shape? It's part of a circle. All right, so there's 4 questions here. And ask you to find the following. So 4 to 4 of f of x dx, 3 to -1 of f of x dx, 1 to 5 of f of x dx, and then this expression, 1 over 7 and subtract -1, integral from -1 to 7 of f of x dx. All right, I think it's your turn. So work on this problem. Now, how do you answer these questions? What kind of shapes do you have? Think of your shapes. What shapes do you see in this picture? Rectangles, triangles, circles. Do you know how to find areas of rectangles, triangles, and circles? Yes. Yes. So the moral here is think about how can I think what I'm looking for in terms of shapes that I know how to find areas for. And yeah, that's the goal. What's the first one? Integral from 4 to 4 of f of x dx. 0. Don't even have to think on that one. How about the integral from 3 to -1 of f of x dx? What do you get? -6, somebody mentioned. Why is it negative? Yeah, the bounds are in the wrong order. So you have to go -1 to 3, and then you have to use your geometry. How about 1 to 5 of f of x dx? Do we have an answer for that one? 10 minus pi. Good. How do we do that? Well, here's how I'm thinking about it. I'm thinking about it as the series of shapes. So I'm going to think of it as the triangle on top of a little rectangle, a big rectangle, subtract part of a circle. So, in other words, you have like this space that you're deleting. So, you say, okay, this is the shape. Imagine that it actually went all the way up here. Then you can count. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, and these 2 halves make 10. Then subtract out a quarter of a circle of radius 2, which is pi. How about this last one? Anybody get that far? I have 1/4 9 minus pi. Oh, no. What can you do? Same thing. Again, imagine that you have negative space. Count your squares up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13 and a half, 14, 15, 16, 17, 18. So there's 18 squares. Don't worry, there's a reason it's 9. There's that factor of 1/8. And then subtract out half the circle, which is 2 pi. So 18 minus 2 pi, but divide by 8. 9 minus pi divided by 4. All right. There we go. Woohoo! Fun times. Now, where are we going? Well, we want to talk about the average value. So if I have a function f of x, I can talk about what's the average value of the function from a to b. And the way you find it is you take 1 over b minus a, integral from a to b of f of x dx. Visually, you can think of it as saying, well, a to b, I can think of it as an area. So I have it shaded here. And now, if I think of it as an average, it's like I'm trying to find a rectangle so that if I just have that constant height, the rectangle has the same area as the function. So that's what we're after, is that height of that rectangle. There is another way to think about this. Normally when you think of averages, so for instance, suppose we have a bunch of quiz scores. Somebody got an 8, somebody got a 9, a couple of people got 10s. How do you find the average quiz score? What's the procedure? Add them all together, divide by how many things you added up. So you say, okay, well, an integral is adding things together. So this integral from a to b of f of x dx, this is adding up all the heights. And you might say, okay, that's a weird way to think about it, but I'll go with that. But now you have to divide by how many things you added up. And that's actually found by the integral a to b of 1 dx. This is how many things were added. But it turns out it's very easy to find the integral from a to b of 1. This is where the b minus a comes from. Okay, so quick example. Find the average value of the function f of x equals 4 minus x squared between 0 and 2. Well, what does that give us? According to the formula, it would be 1 over 2 minus 0, integral 0 to 2 of 4 minus x squared. Well, okay, we can break that up into two integrals. So this is 1/2 integral of 0 to 2 of 4 minus 1/2 integral 0 to 2 of x squared. The first integral, that's not hard to figure out. So if you factor the 4 out, this is 2, and then it's saying integrate from 0 to 2 of 1. And last time we figured out, oh, we can integrate from 0 to 2, or 0 to any number of 1, and the value is the upper bound. Minus 1/2 integral 0 to 2 of x squared. And then we said, last time, because we all take wonderful copious notes, recall the integral from 0 to b of x squared dx. Does anybody remember that? It's 1/3 b cubed. So this would be 1/2 times 1/3 2 cubed. So we end up with 4. And then we can cancel off a 2. So it's 4 subtract 4/3, which is 8/3. All right. Now, what are we going to do with this average value? We're going to introduce a very useful tool, which is called the Mean Value Theorem. And you might say, wait a second, it's too late. You already taught us the Mean Value Theorem. Oh, this is a different Mean Value Theorem. And it says the following. Suppose you have a continuous function between a and b. Then there's some c in the middle where f of c is 1 over b minus a to b of f of x dx. Okay. Why is this true? And can we prove it in the next 4 minutes? Yes. Yes. At least we can argue it. Well, we have a continuous function. And one of the things we talked about is if you have a continuous function on an interval which has the endpoints included, closed and bounded, then that says there's an absolute max and an absolute min. So we'll let m, little m, be the absolute min for f of x on a less than or equal to x less than or equal to b. And big M is almost the same. It's the absolute max. Now, if these are the absolute min and the absolute max, what does it tell us? It tells us that m is less than or equal to f of x is less than or equal to big M. Because the absolute min is as low as it can go. The absolute max is as big as it can go. And then we say, oh, but you know, we talked about properties of integrals. And one of the properties of integrals says that if this is true on the interval, then this implies that little m is less or equal to 1 over b minus a f of x dx, the integral from a to b of f of x dx, is less or equal to big M. So that was our last properties of integrals that we mentioned. And here's the final thing. It says, okay, well, this is the absolute min. This is the absolute max. This is somewhere in the middle. So what's true? If you have a continuous function, you have to get every value in between the absolute min and the absolute max. So something has to match this. There's some f of c that matches. And that's by the what's known as the intermediate value theorem. So that's the mean value theorem, and this is what's going to give us our nice result from next time. I will point out, because this is not the first thing that's had the name intermediate value theorem, do you remember the other intermediate value theorem? Yeah, f prime of c equals f of b minus f of a over b minus a. So here, this was an average, and this says, oh, I match at some point. The average. So again, we have an average, and we're saying we have to match at some point. So they really do line up. There's a reason that they're so close. They're two sides of a coin. That's it for today. We'll pick up again next time.